I'm a systems engineer, and I'd like to talk to you today about how you can take your network from bare metal to a fully provisioned OpenStack cloud in about 25 minutes or so. So I'd like to start off by just talking about how system management for your infrastructure has evolved. And in the very early days, we started off configuring devices on a single machine basis, right? So initially, we started off configuring devices actually at the keyboard or the serial console, and evolved to technologies like Telnet and SSH, so we can remotely configure our devices. We also brought on software package management on a single machine level, whether that was RPMs, DEBs, that kind of thing. That's really now evolved to be centralized management, certainly in the server world at least. So we can use DevOps tools like Puppet and Chef to manage our infrastructure, or centralized configuration and execution tools like Ansible and SaltStack. So what does that really give us? This is really the economic benefit of automation. We heard earlier about how the large cloud providers are really driving this demand because it just needs to be able to function at that scale, right? We have a customer, a large enterprise customer, who at least was using one engineer per every 500 servers that they manage, right? But when you get to the level of the cloud titans, where you're looking at, let's say, 200,000 servers, they have 5 engineers managing those 5 servers. So this works really well in the virtualization world and the server world, all the technologies I mentioned, but for most networks today, the network is lagging behind. The network is the bottleneck. You can see up here, we're using all these modern automation tools for the server world. Why can't we bring those to the networking world? We don't want to still be manually typing the same commands into the CLI that we've always done. So really what I'd like to show you today is how we can make that automation a reality. I'd like to break that automation down into 3 parts. The first is what I call the kind of day zero configuration. How do you initially deploy that network? Then, once it's initially deployed, once it's up and running, how do you maintain that? How do you make config changes automatically? How can you verify those config changes such that you don't introduce human error? That's the second part. And then the third part is really how can we then orchestrate that? How can we integrate that with your virtualization technology such that the network is provisioned automatically? So dividing that into 3 parts, I've got a little challenge for you in this presentation, which is how long do you think we can do each of those aspects? And there'll be answers at the end. So I mentioned the first part of how do we initially provision a network. And there are a number of ways of doing that. And the one technology I'd like to talk to you about today is a technology we have at Arista we call ZTP, Zero Touch Provisioning. So ZTP is really all about bringing the switch from the bare metal up to its base configuration. And how do we do this? Well, I'll go into the little technology details a little bit later, but really what it gives you is the ability to take a switch in a data center, could be a remote hands, they don't need to know anything about networking configuration, plug the device in, and it's actually being configured by itself, right? And this benefit of automation brings, reducing human error, not needing the NetOps skills on site, and we can do this all remotely as well. So we've actually packaged this into a open source piece of software you can download from GitHub. We call ZTP Server. And what this really gives you is the functionality to host all of this on a remote server to let you automatically provision these devices. How does it look? Well, it's really split into two parts. It's a client and server operation. So you can think of your network devices, switches, as a client, and they're connecting to this server. So on the server, it is a very simple application in that respect. You can run it on any x86 machine. You can run it as a VM. And that will then communicate with the ZTP process on the network switch. So we can then customize this quite an interesting way, which is we can define templates of how we want to validate the topology of our network, right? So this is maybe a complex example. We have a leaf switch or a spine switch. We can actually work out what that device is based on its neighbor information, right? There's a protocol called LLDP, the Link Layer Discovery Protocol. We can actually use that to work out what its neighbors are, and based on that, where it is in the network, and build our configuration accordingly. We can then define what we call definitions, which is just a very simple templated set of actions we can take. So this action could be, for example, enforcing the software version. What particular version of software do we want this device to run? That's a very simple example, but we can actually bring this down to the full initial configuration that we need. So depending on the type of switch, if it's supporting servers, if it's supporting storage, we can apply a different configuration from day zero. And this workflow just outlines how the process will work. So initially, when the switch boots up, if you take a switch out of the box in the factory, it's in this mode. And the way it works, technically, is it will send a DHCP request on all ports, and when it receives a DHCP response with an option field, it can connect to the server based on that information. When it connects to the server can then decide, have we seen this device before? If we haven't, if it's a new device, we can then build its topology, as I mentioned earlier, so we know where it is in the network. Once we know where it is in the network, we can build its configuration. Right? So it's a very simple format, and that configuration is built from a very simple set of templates. So one template might be the resource pool. So we define a pool of management IP addresses we can use. Likewise, host names, interface descriptions, all of that necessary config can be templated and can be automated. So what sort of thing we can do? As I say, pretty much every configuration you would be able to make to the switch. So we have an action called add config, fairly self-explanatory, which allows you to add any part of switch configuration automatically. But we can also do some clever things like copy files to the switch. If you've got particular extensions you can use, we can copy those from day zero. Likewise, we can do things like send email and run scripts. So it's really very flexible and very powerful in allowing you from day zero to bring your network device up how you want. So as I mentioned earlier, you can define your templates, define your resource pools, and then those pools can be allocated to that template. So the simple example of the management IP address, we can merely take that management subnet and apply it in the config. In this particular case, these are flat files, but you've got to remember this is just software, and it's very customizable. It's very customizable not only by ourselves, but also by our wide network community. So, for example, instead of using a flat file for your IP address allocation, you could hook into the API of your IP address management solution. So you're dynamically getting the right IP addresses with the way, the infrastructure you want. And another interesting application of this is something we call zero-touch replacement, right? Which is exactly the same process, but just when a device fails. So firstly, we can use the ZTP server to have regular backups of your network device config. And once you have that, it's very then easy when a device needs to be replaced. Let's say there's a hardware failure, that can also be fully automated. So I always want to do a demo, basically, where I take a network switch live, shoot it. Funny enough, I'm not allowed to do that, but essentially destroy the switch and then put another one right in its place, and you'll see how the entire configuration can be automatically mirrored to the replaced device. So I know there's a lot of slides there, maybe a lot of technical content, but I'd just like to give you a little demonstration of how this would work in practice. So this is the normal boot process of an Arista switch. There's nothing new here. It's booting into the Linux kernel, which all of the devices are built on. So we're built on top of a stock Linux kernel, which has been unmodified, and then all the processes are loaded into user space. And this part of the boot process is the same no matter what device it is. But fresh out of the box, it boots into this special ZTP mode, if I will. And this mode is entered if there's no configuration. So if the config file is empty or does not exist, it will boot into this mode. While I just wait for the device to boot. Here we go. So you will see here, no startup config has been found, right? If no startup config has been found, then we go into the zero-touch provisioning mode. And what we're doing is we're sending out that DHCP request on all ports. And that DHCP request will continue to be sent until it receives a response with a server it can connect to. Okay, great. So we can then see it's found its LLDP neighbors. So it's found that there's a device connected to the management interface. Very simple network in this case. Yep, so it's sending that DHCP request out of all of its ports. And received a file bootscript.py. So in this particular case, we're using a Python script to build that configuration, but it doesn't have to be. It could be any form of automation you will. If you're using a DevOps tool like Chef, Ansible, and Puppet, which I'll be talking about later on today, you can use those tools as well. So we can see once it's got a DHCP response, it's downloaded the script and executing the script. Let's see what it does. So that script is checking the version of the software, and that version isn't on the switch, isn't the correct version we want. So what it can then do is dynamically pull the correct software version image from that server, and then reload. Okay, so I'm not going to wait for the full boot process here, but essentially what happens is we do a full reboot, and we've already copied the new software image, so we're running the new software, and we have all of the necessary config that we need. So using ZTP, to summarize, we can do all of that full day zero configuration in an automated fashion, in a remote fashion, without having any specialist network skills on site. So once we've got this device set up, great, it works. Do we need to touch it again? Probably. So to use one example of kind of ongoing day-to-day management, I'd like to talk about the DevOps tools. And this is really a small teaser of what I'll be talking in a deep dive about later today. But just to give you an idea, presumably you've all heard of DevOps, development meets operations. But the best way I like to think of it is infrastructure as code, right? Infrastructure as source code. So you're defining in a programmatic way, using software, how you want your infrastructure to look. Now, I'm not going to talk about this in too much detail from the infrastructure sense. I'm sure there's many more smarter people in the room than me who know about this. But I'd like to just talk about how we can then bring that to the field of networking. So just to use one example today, I'm going to talk about Ansible, but all of these principles apply to the likes of Chef, of Puppet, and Salt, and such like. So the nice thing about Ansible as one of these tools is it's quite lightweight, which works well for a network device, which is not always a fully fledged server. It's based on Python, so anyone familiar with Python, it's very easy to get used to, and it can be hosted on any regular server. So from that point of view, it works really well. And you can define these templates in a very standardized form, whether that's this YAML format or JSON. But how does that work in the networking space? Well, on our devices at least, we've written some EOS, being our operating system, we've written some EOS roles for Ansible. So what that does is it actually uses our API on the device. So all of our devices have a very standards-based, JSON-based API to configure them. And the Ansible roles are basically leveraging that API. Then what we can do is, with those roles, do quite a wide range of network configuration via Ansible. How to install the EOS roles is very, very simple. You can take any regular Ansible deployment and just add the EOS roles. Once you've done that, you then have access to all of the Arista libraries, which gives you a full range of configuration options on the device. So to give you a demo, I'm going to run a playbook, which is designed to configure some interfaces facing a server. So when we provision a new server in the data center, there's usually some network configuration attached to that. In this case, we're going to provision some interface descriptions and some VLAN information. Now, this has been defined in a YAML format, very easy standards-based structured format, and you should be able to see the EOS roles there. So, for example, EOS underscore interface defines a switch interface. EOS underscore VLAN defines a VLAN. So I'm just going to show you now how we can create those roles. So you just saw the playbook, how it was defined. I'm going to run that playbook now. So we're giving the playbook with a list of hosts to connect to. So that -i hosts, it's going a little too quickly, but we define which switches we want to execute it on, and give it the playbook, and it will just go and execute. So here's an Arista switch. If I do a show running config, this switch has been brought up from bare metal by ZTP, and it has a fairly basic configuration. It has all the basic things it needs, but you'll see it doesn't have any interface config on. So what I'm going to do is do a command called the watch command, which continually polls the configuration, so we'll be able to see the change. So right now, as you can see, on interfaces Ethernet 3 and Ethernet 4, there is no configuration right now. Yep. So what I'm then going to do is go back to the server and configure I'll execute the Ansible script. And what this script is doing, as you'll see it going past, is it's going to every device, including this one switch, and configuring the necessary interface descriptions, configuring the necessary VLANs, and the necessary port config. So we'll see now, all of this configuration has been created through Ansible. So the description and the switch port config, those VLANs, have all been configured through Ansible, which is kind of cool, right? So far, from day 0 to sometime in the future of provisioning a new server, all of these changes have been made without actually touching the switch CLI. So you get all those benefits of scale, all those benefits of automation, reducing human error, managing a network device like a server, all of those benefits. And then going on day to day, how do we enforce that policy, right? So I talked about infrastructure as source code. So we've defined how we want our network to look. How do we enforce that on an ongoing basis? Well, let's pretend on that network I just configured, I make a human error. I make a typo. So this is the existing config. I'm going to set a bad description. So description wrong, okay? So this is a very simple example of human error. Yep. This is clearly wrong. Someone's made a mistake on the network. How do we enforce that? Using Ansible. Well, Ansible has quite rich config and execution management. And what we can do is essentially just rerun our original provisioning script, right? Because we've defined in the code how we want this to look. So if I do the ---- check flag, this will essentially check the configuration without actually applying it yet. And you'll see in yellow there that there's something we don't expect. We can get this going. Right, so you should be able to see that our description is wrong. And yeah, we can see one part of the configuration has changed where it shouldn't be. So if we just run that script again, but without the ---- check flag, then it will go ahead and execute that change. So we can see we've changed it there, and our configuration is now back to normal. So, and we can verify that at the actual switch command line, the description has been restored to what it should be. So I suppose that part gives our ongoing configuration change, configuration management, and execution in an automated fashion. Okay, that's great. We have a question. Please.
So let's say in this case you launch this script and was configuration change that you have found by the way.
Yes.
But is there any change to have like an event-driven configuration push? So if you configure the switch
Yes.
in a good manner or not, like sends an event saying, hey, my configuration doesn't change, and automatically launches this configuration check, or do you have to always do it on your own?
Yeah, certainly. So I can't speak for all network devices, but certainly on Arista, we have an event handler that can essentially execute any script when a change has been made. So in that case, if I made the wrong description, you could have a script that essentially calls the server. Let's say the server's running Ansible. The script could call the server and re-execute the check script. Now, of course, you might not want it fully automated. So what you could do is you could have the check script email you, and then based on that email, you could decide to change the execution. So really, it's very powerful, and that comes from this principle of infrastructure as source code, right? At the end of the day, it's just software, so we can be very powerful about how we do this. But one thing you might have noticed about this is still distinct from the server infrastructure. Right? We're managing our network like a server, but it's not fully integrated, it's not orchestrated. So I'd like to then talk about the third part of how we do that. So in that case, I'm choosing OpenStack for this piece. This is, of course, one example of a controller, one example of an orchestration tool. It doesn't have to be. We can use commercial products as well. But for any of you not familiar with OpenStack, this is not a presentation on OpenStack, but just as a very quick summary, it's best described as a cloud operating system. Right? So OpenStack provides various components for automating and managing compute and storage and various aspects of a cloud. But the part I'm interested in from a networking point of view is the networking component. And the networking component is this part called Neutron. Right? So Neutron is the component within this cloud OS that handles all of the networking config, right? And there's three parts to this, essentially. There's a layer 2 plugin, which handles your switching, your distributed switches, your VLANs, that sort of thing. There's a layer 3 plugin that handles your routing, so how do tenant networks get out into the outside world and be able to talk to each other. And then there's a services plugin, which covers the higher layers, so layer 4 through 7. The bit I'll be focusing on today, although Arista offers integration with both the layer 2 and the layer 3 plugin, is layer 2. So within the layer 2 part of this, So within the layer 2 part of this, we actually co-authored a driver we call ML2, the driver plugin we called ML2. And this allows the layer 2 part of OpenStack to communicate with network devices, right? So you can load a vendor-specific driver. So let's say, in this case, an Arista driver that allows OpenStack to be fully integrated with the physical network and configure those physical devices. Right? So that's providing that rich end-to-end stack from a config point of view, from a visibility point of view, that we can actually, from one point, from one controller, control both the physical and the virtual network. How does this work? As I've talked about the ML2 plugin, that ML2 plugin uses an Arista driver, and that Arista driver can then talk to the network to do the provisioning. On the Arista side, we can build a full topology of the network, so we know exactly what the network looks like, and not only that, but what servers are connected where. So our integration with OpenStack, again, uses this open, standards-based LLDP protocol to work out what OpenStack host is where on the network. So straight off, even if we're not doing any changes, any configuration, we can still know where hosts are on the network, and from that deduce what VM is where on the network. When it becomes really powerful, though, is when we can make changes. And how that works is, again, it's built on our OpenE API. So the driver within OpenStack will use this API to communicate with the network and make configuration changes. So the first part was kind of network configuration. So we can initially create tenant networks. And then the second part is actually provisioning the network for new hosts, new VMs on the network. And this can be two ways from a layer 2 perspective. The part you're probably most familiar with is VLAN based. So we're provisioning simple VLANs on the devices. This is very straightforward, very simple from a complexity point of view. But there's some limitations to VLANs, right? The first one is mostly scale. So firstly, you're limited to 4,000 tenant networks. But not only that, you're also limited to your network design, right? This network design you can see is what we call a layer 2 fabric, where there's no routing between the network devices. So we're spanning those VLANs across the network. And that works well from a simple point of view, but works less well from a scale point of view. So what we are really helping the industry bring is the VXLAN standard, co-authored by ourselves, VMware, and others. And really, this is allowing you to scale across a layer 2 network. Right, so we're breaking out of that 4,000 VLAN limitation, and we can actually scale to 16 million VXLAN identifiers. And what that really allows you to do is build a fully automated, multi-tenanted cloud network, right? So we can have multiple OpenStack deployments running over the same physical infrastructure, and that works really well. So what I'd like to do now is actually skip to a brief demonstration of how this works. Okay. So for those of you not familiar with OpenStack, this is as simple as you can get. This is a base DevStack installation of OpenStack, and this is the GUI, the Horizon dashboard. That would help. Thank you. Bear with me. So arrangement mirrored. Try this. Okay, perfect. Change the resolution. Scale. Cool. We can all see that, I hope. So this is the very basic deployment. The only network we have in our cloud so far is the management network, the public network. So what I'm going to do is create a new network and log in. I'm going to call this network 1. And when I create a new tenant network, I can assign a subnet to it, subnet 1, and we're going to pick a range of network addresses for it. 13 is always my lucky number. So I've created that network, that tenant on the OpenStack side, and you'll be able to see how that can integrate with the physical network. So I'm going to log into this device if it isn't already. The Wi-Fi was working very quickly earlier, and of course is less so now. Sorry about this. So I have some connectivity. So I'm going to change from the Wi-Fi to some 3G tethering. Okay. Let's try this. Always the case with a live demo. Okay, great. So we seem to be connected. Let's see if I can connect to the network device. Okay, I am connecting, but incredibly slowly, so please forgive the lag. So where was I? I've just created a network within OpenStack. We can show you how that tenant network has been integrated with the physical network. So if I run a command on the switch, show OpenStack networks, we can see that network I created has automatically been mirrored on the physical network side. You'll see this network has two identifiers. 502 represents the VLAN number, which is down to the host. And then we're mapping to a VXLAN identifier, which we're using northbound for those scale benefits I mentioned earlier. Once we've created the network, we can actually put a compute instance on that network. So it is working just incredibly slowly. But of course, much faster than if you were making network configurations in a manual fashion. So I'm going to create a new virtual machine instance. I'm going to call it VM1 and select an image to boot from. Very simple image. So on the networking tab, I have a list of available tenant networks. I can place this VM in. I only have one network right now, so I'm going to use that. And so what I'm going to do is spin up a compute instance. So I thought I selected a network. What was that? Okay. I think I'm having some connectivity problems. So I think what I shall do is just explain. I'm very sorry that live demos are always very tricky. However, at Arista, we do have a stand outside. So if you'd like to see me show this in more detail, I'm more than happy to spend the time and demo this to you outside. But essentially what I was trying to show is how we can dynamically create all of the necessary network config for tenant network creation and virtual machine creation on the switch, again, with no manual CLI intervention, all being provisioned through OpenStack. And we can do that in a fully automated fashion, right? And not only can we do it at a layer 2 level, so VLAN, VXLAN, provisioning, port config, we can also provision the layer 3. So if you wish, that integration between the physical and virtual network, from a routing perspective, we can do that too. So I'm conscious of time as well. So I suppose to wrap up, I asked this question of how long? How can we actually do this end-to-end? Take a bare metal network device, provision it with remotely with zero touch, do this day-to-day config change management, so use Ansible to deploy on top, and then provision this fully automated network cloud. Well, the answers to that, when you have good quality internet connectivity, Wi-Fi that is working, it's usually, we can do it in just about under 23 minutes. So that's breaking up roughly equal time for each of those aspects. The zero-touch provisioning, the first part, often varies on boot time, but really we can do that end-to-end provisioning to build a cloud in a very, very short space of time. And you've got to remember these numbers as well can be done in parallel. So if you have a network of 100 switches, it's going to be hardly any longer to provision those 100 switches in an automated fashion than it is to do one. So if you're looking at building any networks of scale, I recommend you look at these automation technologies. And if you'd like to hear more about how we at Arista can help you do that, come speak to us at the stand outside. So thank you very much. Are there any questions? No questions? Well, thank you very much for your time. Thank you.